Welcome back to our second session of this mini workshop on Python programming. I will be sharing my screen here. Okay. So this is the idea. Let me see. I will be sharing with you the links for the materials. This is the front page of the workshop for the big workshop and the mini workshops. And this is, which is basically, now I correct the links, so now they are pointing to the right places, I think. And this one here is the main materials, the content of the material. Right here. We'll be sharing here, this one. Okay. And today we will be covering, as we mentioned before, two important aspects of Python when you use it for scripting purposes in scientific situations, which is NumPy, which is the de facto standard for numerical processing, and Pandas, which is an important package in data analysis, which is important for many people. So we will be discussing those two. I skip entirely, and we have notebooks for that. I will point you for all the notebooks because this was part of a bigger workshop. I'm skipping the part from Matplotlib, but if you want, you can go and say, oh, I didn't fix this. Okay, I need to see what. For pandas and NumPy, and I skip the Matplotlib. So if you want, this is pretty much the content of the notebook reconverted into the text. So here is a static vision of the content of the notebook, and I noticed that I made a mistake somewhere in the content of this part. But what we will actually doing is to look into the notebooks themselves, so the actual notebooks. So if you want to reproduce that, I will go really quickly into the procedure here. Let's see. First, you go into Turning Flat, Open on Demand. We will be doing everything with Jupyter Notebooks. So this is the link. I will be posting this link. So avoid this. And you just copy this. So this is the link that you can use to access Turning Flat. Once you do that, go here and click here or click in Interactive Apps. And after click in Jupyter Official Images. Last time, Wednesday, we noticed that some of the module-based Jupyter notebooks were missing the equation. So there is something that is missing on that side, but it's in here. If you select any of those Jupyter notebooks, which are the official ones, and they have notebooks for various data mining, data processing things, data science related notebooks. So select one. I just picking the first one, and after that I select standby, 4 hours, ACPU cores, no GPUs, Jupyter Lab. Click on launch. When you do that, you land on something like this. You get something like this. And after a few seconds, you will see this button here. When you click in this button, you will be opening this. Well, I'll keep it later. So to get all the material, what you do is to click in clusters and click here in turning flat shell axis. You will get in something like this. And here you execute this command. So I will be pasting all those links. So if you have not done so, so here you are downloading all the materials. And I am doing this right here on my home folder. So now I can open the notebooks and play with them. So here you will see, well, I have many things here, but you will see a folder called notebooks. This Python, and we will be start with the NumPy. So what I'm skipping, yesterday I rushed into this chapter 3, which is just an introduction of a set of packages for scientific computing in Python. So just an overview, a quick overview of all of them. And I also kind of rush on the standard library. You can follow that. So this time I will go calmly into the NumPy, which is often used for post-processing, for generating plots, for manipulating results of simulations. I will be skipping the matplotlib, but if you want, once you have it here, you can open it and you can follow. And there are over the internet far more materials about explaining all these, the plotting capabilities of matplotlib. So this is not so hard to learn about. And finally, I will be, and also skipping SciPy. Not everybody, but let's say what I'm doing here is pretty much the same what I did for the general scientific packages. I am making a selection, kind of personal selection, of what I find often used from SciPy for scientific computing. So the list of modules inside SciPy is big. Not everybody uses the same things for the same purposes. So I am just picking a few of those and making examples. So the special functions, the spatial module, integration, interpolation, linear algebra, a few things like that. So, but I am skipping that section here too. And at the end, on the second hour, I will be working with pandas. So, which is a library for data analysis. So that's pretty much what we will be covering today. And also the final sections are also skipped, the Cython and the parallel programming with Python. And so in reality, we will be covering 1, portion of 2, 4, and 6, and 7. So let's try to discard this. And especially I want to concentrate on NumPy, which is, it could be confusing initially. Okay. Again, this is oriented toward scripting. So relatively a small code that you write on your Jupyter notebook, because what you want to do is not to build a program, but more likely a script that will post-process at the output of simulations, execution, making some plots, getting those plots in a good file format, because they will go directly into publications, into papers. That is the idea. So for that, I am covering the NumPy, which is the basic architecture for multidimensional arrays, and pandas, which is also used for post-processing data analysis purposes. So let's start with NumPy. Let me see if I can get this. Okay. So this is the idea. We'll start around here. remember that in our first session, we discussed about the fundamentals of the language, the Python as a programming language, or like a traditional programming language. You need to know how to store variables, how to store data in variables, how to make loops, so repeat operations over and over, conditional, so bifurcate the execution depending on some expressions, and printing and I/O, so input and output from the language. Using the language for doing input and output. Now, when I would discuss the variables, I told you, okay, there are ways you can store integers, floating point numbers. Python is very flexible with those things. And there are a few other entities that allow you to store multiple values under a single name, like lists, sequences, tuples, dictionaries, all that. And one of the things that I mentioned at that moment was that lists are very easy to use. They are relatively cheap, very simple to use. You can just stack a few values and you can add more values to that. They don't need to have the same type. So you can put a number in the list, and the next element in the list is a word. And after you put a complex number, and list can be really, really flexible. But that flexibility comes with a price, and that is performance. If you really are dealing with a lot of numerical data, you don't want to store that data using list or list of lists or matrices or things like that. This is not the most efficient way. The same thing happens with dictionaries. With dictionaries, you can have a key value pair, and the key could be basically anything, and the value could be also be a list, or could be just could be an image, could be many things, could be an object in general. So now, again, lists, dictionaries are not, you should not be your tool to store numerical data, large amount of numerical data, if you are really planning to manipulate that seriously. So NumPy is not part of the language, it's not part of the standard library, but it's pretty much the de facto standard for manipulating large numbers of multidimensional arrays. Now, when we talk about multidimensional array, the first thing that we need to know is that on a multidimensional array, which is like a vector or a matrix, or all the elements on that array, on that matrix, must be of the same kind. That is one of the restrictions. All of them are, if they are real numbers, all of them are real numbers. If you are storing an integer there, the integer will be converted into a real number, into a decimal number, the decimal point. That is one limitation, or one of the characteristics of that. Another point is that everything that you are doing with NumPy, at the end of the day, is not the objects created, or those NumPy are, at the end of the day, they are no Python. Those routines that manipulate the numerical arrays, the matrices, doesn't need to be a two-dimensional matrix. It could be a multi-dimensional object. Are written in C and Fortran. They are very, very efficient, has been developed since the 70s. So most of NumPy actually relies on a couple of libraries that are widely used in scientific computing, which are BLAS and LAPACK. BLAS and LAPACK, BLAS is basic linear algebra subroutines. And those are libraries, again, written back in the 70s and developed during the 80s. And today with the parallelization, they add the multi-core parallelization to those things. They have been improving. And they do basic linear algebra stuff, like vector matrix multiplications, matrix multiplications, all those basic operations like vector multiplication plus and the addition of another vector, that they have routines for dealing with that. Very basic routines and very efficient. And some vendors like Intel, those who produce processors, they offer their optimized versions of those libraries for their own processors. So that's another thing that happens with that. And LAPACK, the second library, BLAS is that basic linear algebra stuff. LAPACK uses BLAS to do more complex operations in linear algebra. For example, inverting a matrix, computing the eigenvalues and eigenvectors of a matrix, doing triangular decompositions, all those sort of things that at the end of the day are translated in a set of basic linear algebra operations, matrix multiplications or swapping rows and or columns. All those basic things are used to produce more complex linear algebra. So if you need to know the eigenvalues, eigenvectors of a given matrix, you will be using LAPACK, and that LAPACK, those LAPACK routines, they will be using BLAS. And those BLAS routines, they have versions for single precision, double precision, complex numbers, double complex numbers. So they have a plethora of different variants of those routines. And NumPy is simply hiding all that behind a Python layer where you work with that without realizing if something needs to be converted into a complex or single precision or double precision. That is the beauty of NumPy. It's hiding all that from you. But you should be aware that that thing is happening. So it's not using lists, it's not using dictionaries, it's using something else far more efficient. And for that reason, NumPy is significantly faster than anything that you can do with pure Py, because at the end of the day, you are not using Py. So that's what I'm mentioning there. Also, again, NumPy is the foundation for many other libraries, the other scientific libraries at higher levels. So matplotlib, which is the library for plotting, executes on top of NumPy arrays. So some things, even if you can provide a list, at the end of the day, matplotlib is reconverting all those things into NumPy arrays, so for processing that internally. So Pandas, for example, is also working on top of NumPy. So NumPy is the first strata in numerical processing, and there are many other packages on top of that for doing real scientific computing. So it's important to understand well how you create NumPy arrays, how you manipulate those arrays, how you cut them, how you play with those things with confidence, with workable knowledge of those things. That's the purpose of this. This is a lecture for, especially for the scripting, and for scientific scripting, this is the kind of thing that you want to learn and learn well. Okay, so now what I'm doing here is a little bit demonstrating you what happens when you use lists. And I have here like a product between what I'm doing here. Okay, so I'm having two lists of values, 1 million elements, 1 million elements here. And I am creating in a very crude way a list to a couple of lists of numbers. I have the list, the same values in reverse order. I have two lists. And the whole purpose here is to demonstrate what happens if I try to work with those lists for making the product, the dot product. So the product of two vectors, two long vectors. So this is what happens if I can make the product and I can compute, okay, I can see what's going on with that. There is a tool in Jupyter notebooks that allow me to test the timing for a function on the notebook, and this time IT. So when I execute that, and then I probably execute it on Thorny, so probably the numbers will be really similar. This is what I got. So computing this dot product of two long 1 million dimension vector, it takes 98 milliseconds. What it's doing is computing that many times, and you get the median, the standard deviation. You get, but let's focus just in the mid. So 98.1 milliseconds. Doesn't look much. Okay, who cares about a few milliseconds? But when you are doing this over and over with bigger structure, it's not a vector, it's just it's a matrix, multi-dimensional array. Those milliseconds start adding up, and now it becomes seconds, after become minutes. And when you are doing this over and over, one code that could take few hours can be executed in NumPy in a few minutes or even seconds. So that is the purpose of this. So this is the worst case scenario, is working directly with arrays. That is what I'm doing here. Now, what I'm doing here is half of the way of that is taking the list, the Python list, and convert that into a NumPy array. This is how you convert from a list, from any iterable, that's the technical name, that converted into a list. Again, one of the things is all those numbers and the way I create those are integer numbers. There's no big problem with that. So there will be NumPy arrays of integer numbers, 1 million. So before manipulating that, I am converting those into NumPy arrays. I am making the product of them. Okay, that is what I'm doing. I'm getting exactly the same result. But this time, if I compute the timing of that, well, it's a little bit less. So I got 1 millisecond of advantage. Not much, but still. So now, what I'm doing next is to work directly, build those things as NumPy arrays, making the product. So inserting now the already created NumPy arrays into a function that the only thing that is doing is computing the dot product. And the dot product for vectors in NumPy is just the start. It's just the product. NumPy knows how to deal with a couple of vectors. And they will do the operation. And depending if you are in behind curtains, you are using a serial version of the linear algebra routines or not, it will give you slightly different numbers. But in any case, it will be much better than executing that with list. That is the main message that I want to offer you. You reduce this from 98 milliseconds back to 97 milliseconds. And if you are doing this in pure NumPy arrays, now it's 1.9 milliseconds. That is what you should keep in mind. For numerical operations, I should, from the very beginning, start working with NumPy arrays. Period. It's the best. It's the best that you can do with Python. And now just to cover the overhead on the creation of this array, because now this function is so small that you don't need to use the function. So I'm replacing that for just the operation itself, 8 times b. And it lowers a little bit more. So it's now 1.86 milliseconds. So you see, working with NumPy give you an advantage. The alternative to that is to write the entire operation into something like C or Fortran, and this is what I'm doing here. So if you want to do that, well, you will have some extra code for importing libraries, for building the code. In Fortran and C, you have to put more stuff. But just the portion that is doing the math is this in C, is write this. And you will get something very similar, but you have to type a lot of code for getting just that. So NumPy is alleviating you on that side. You don't have to write code in Fortran or C, and if you do it right, you will be gaining a lot of performance on that. By the way, in the case, this is in C. In C, you need to be explicit on the looping. In Fortran, as that language was especially created, it's a Fortran translator, a formula translator. That's the original name. That is where the name comes from. That was a programming language created by scientists for scientists. So in that language, the operation, the vector multiplication is integrated. It will do that. So you can skip the loop. The loop will happen inside. And if again with Fortran and C, you can parallelize on multiple cores, and that's why you can reduce so heavily the burden on the execution. You can use all the cores, if possible, all the cores in your computer, and you are basically cutting the amount of time by the number of cores. But still, if you're using just one core, just the fact that you are using something that at that low level give you an extreme advantage. Let me see. So here I am comparing again what you can do. With two arrays, like an example of a small code written in just with numbers. Okay, and the timings for there. Okay, and now in new architectures, there are things that you can move beyond that. Is that you can use either the multiple cores on a CPU or express those operations and execute those operations instead of executing those on the CPUs to export that load to a GPU, to an external accelerator. And this is exactly what those codes for deep learning, for neural networks, for artificial intelligence are doing. Though artificial intelligence, or the big chunk of artificial intelligence that you see today for deep learning, all that, is basically linear algebra. It's no more than linear algebra. A very simple and boring linear algebra with a lot of twists, a few non-linearities here and there, but it's something that can be executed very, very efficiently on a GPU. So that is another thing that give you that. And here I am making another example, slightly different. I have a matrix here. So this is a vector, random numbers, floating point number, and this is a matrix. And what I'm doing here is computing the timing of this operation here, the dot product. So I am computing the difference in time, or some other operation here next exponentiating the argument, the array. So you see, it's really, really efficient when you work with this library. So for now that I hope convince you that is the NumPy serves a good purpose and is something that you should learn when you are post-processing, pre-processing, or even if the program is itself entirely, if your research is manipulating this. Now you need to learn a few things: how you create arrays, how you modify arrays, how you take portions of an array. So this the creation, manipulation, and slicing of array are the first skills that you need to gather before we can move into more advanced stuff. So let's deal with that. Except for the slicing, this first part are trivial. Let's start with the creation of arrays. So NumPy offers you a few very reasonable amount of routines for array creation. So you can do it by hand. So you have a list, you have something that NumPy can convert into a NumPy array. That's one way of doing it. You can see the typing of that. So you can create NumPy arrays that way. And also, once you have created those, you can just change one particular element just by addressing that element in particular. In NumPy, follows the C convention, if you like. In Fortran, there are both ways, but so everything in Python starts from 0. So the first element is the element with the index number 0. So what I'm doing here is I create an array 1, 2, 3. Here I am changing the first element in the array, and is the number 5. Another nuance of this is that in NumPy arrays, you cannot do what you do in lists, that is appending elements at the end. You can do that, but what is happening is you are creating a new array. You are all the time creating a new object. While in the lists, they work easier with that. You can just append elements at the end, and you can stack more elements. Here, at the very beginning, you need to decide the size of the array, start filling with values, and if you need to enlarge it, you can do it, but it's creating an entire new array. So here, same thing for a two-dimensional array. So you can think about that. It doesn't matter if you consider that way or not. This is like 2-row array, 2 rows, 3 columns. So that's how this looks like. And you can ask, the first thing is the shape of an array. It doesn't need to be 2-dimensional. This is an array that is 2-dimensional in particular, but it has 2 rows. So in the first index runs in 2 values, and the second index in the array runs for 3 values, the 0, 1, and 2. Those are. So this element here, the 1 here, is the element 0, 0, and the element here is the element 1, 2. Okay, so now here I am picking some of those elements to demonstrate how you can index those, so you can address those elements. Beyond that, beyond the manual creation from something that is not a NumPy array into a NumPy array, a list or a sequence or something that is an iterable, something that you can count and you can reconvert into a NumPy array. And there are also routines for building, let's say, simple arrays, like an array full of zeros, an array full of ones here, and an array with a certain constant everywhere. Those are routines and that allow you to create all those things. And the I is like a diagonal, a purely diagonal All right. Now, so here I am demonstrating more things like and the ones. Now, another thing that you can do with that, with those arrays, is then is creating a new array, is to having a couple of arrays and you can stack them. So attach more rows or more columns to an array. So what I'm doing here is I have this array, D, that is 3 times 2, an array. And I created another array where I am multiplying by 2 here. And I stacking that on the first index. Which is also called a vertical stacking. There's the V stack. That's one thing that you can do. Another thing that you can do is stack the array horizontally. You have an array, another array. This time you are stacking on the second index, and the first index is the rows. The second index, at least for those two-dimensional things, will be the columns, and you can stack those either vertically by the rows or horizontally by the columns. You know, the columns will be and now here together. Another creation method here for random matrices. And by the way, all what we are doing here are dense linear algebra. So NumPy is dealing with arrays where you expect most of the elements will contain non-zero values. If you really are dealing with sparse matrices, there are other routines, some of them in NumPy, but not all. And the support for that is much small. But in SciPy, there is something more for dealing with the sparse matrices. So big matrices could be 1 million times 1 million, when only 0.1% of the elements there are non-zero. So there are special routines for dealing with the sparse arrays, and we are not covering that here. That is a special topic on itself. Okay, so now that is the creation. And there is this one, which is also very often used. When you want to create like to create like an array where you are jumping with a constant jump from 0 to 10, and you want 8 elements fit between that in that range. Well, linspace will create a linear spacing on between those two extremes. So between 0 to 10 will put 8 values there. So all those are creation routines. So that is the first skill. So you learn that, you know how to deal with that. Good. Now, what for most people is the trickiest part of NumPy are understanding the indexing. Well, that's relatively easy, but especially, and I will devote most of the time here on the slicing, which is the slicing and the strike. And this is important, and it's good. It's good to devote some time and go into this carefully, because it's important and sometimes not so clear at the very beginning. So now what I'm doing is I'm creating a very simple array here that allow me to see very clearly what I'm doing. So I'm creating here a 3 times 4 array. So you see here, if you want, I can take one element. So this is the number first row. So this number 2 here is in the first row, second column. So the element for that is the 0, 1 element, for example. And now what I'm doing is cutting, for example, all the columns here up to the column number 2. the first two columns, and from skipping the row 1 up to before the row 3. So if you want to know how many rows and columns we have here, all that you have to do is imagine that instead of just the column, you have a 0. It's 0, column 2. First thing to replace in mind, to have in mind, from 0 to 2. How many columns are there? You just make the subtraction. We are talking about two rows here. So the first 2 rows, and from 1 to 3, it's not covered, it's not including the number 1. So how many are here? Just 2. So we are cutting just 2 rows and 2 columns. Which rows and columns? I am dealing with these columns up to number 2 here. This one and this one. The first row, sorry. So the first cut here, this column 2 is cutting me just the first row, the first 2 rows. One thing. Now, the next thing that I'm doing here is cutting columns 1 to 3. So skipping this, it will be not covering the number 3, which is the 4th column, and not including the first column here. So it's covering this to here. So 2, 3, 6, 7, as you see here. And that is an slicing. When you are doing this, what you have is just a viewing a portion of that. It's not creating a new array. NumPy tries as much as possible to not start duplicating the array so quick, because those arrays could be big and you want to be as efficient as possible. So making copies is very inefficient. So this is just a slice. It's just a view of a portion of an array. If you put the name of that, start editing that, you are editing the original array. So the terminology for that is those are references. So this is just a portion of this array, a tiny portion. These 4 elements here that are encapsulated. Now, okay, this is the message that I was telling you about. And it slides, this small cut, is not that it's taking the values and give you a new variable. It's just giving you a visual or representation of that section of the array. But if you edit the values there, you are editing the whole array, the original array. And that's exactly what I'm doing here. I am taking the array for B. That is something that I'm calling B. So B is this slice, and I'm editing one of the values on the slides, and I still editing the original array here. Okay, so something to keep in mind. Let me see what I can move. Okay, there is this thing that also is very common. You can read the other parts. Let's try to concentrate on what I often use. You can have an array, and you can take the same elements and reshape the array, change the dimensions of the array. So here, up to this point, this is a long and unidimensional array with 100 elements, from 0 to 99. What I'm doing here is changing the array into a 10 by 10 array. And you can do that for 2 dimensions, 3 dimensions, 4 dimensions, no matter what. As soon as you preserve the number of elements is consistent with your arrangements. If you have uh, uh, 100 elements, you can do 10 by 10, you can do 20 by 20 times 5 or whatever, but you will have 100 elements. So this is what I'm doing here. And now here I'm demonstrating on one particular slice, one particular slice here. What I'm cutting, this element here, the 19, this here, here in reverse order. So here I am going backwards, so like going like this. This is the first element that I'm doing. I am moving backwards, that's the meaning of this -1. How I am moving into the array, and I am cutting also from the 69, this array here, backwards. So I am cutting this, the number 1 here. Okay. Row number 1, which is the second row, the index number 1. The index number 1 is the second row, that's it here. And the 5, which is this one here. I'm taking all the elements backwards. Again, this is just a view of the array. I edit that, I will be editing the original one. More reshapes. I have here another example. And arrange 6 values, and I am reshaping that, adding an extra dimension for an element where I only have 1. So 2 times 3 times 1. So basically, I'm taking the final there and putting inside a big bear. So there is just 1 element in the final. For each of those in the final index are corresponding to this square brackets. It's picking just the final. There is just 1 element. If I don't use this comma 1 here, all those 0, 1, and 2, they will be isolated. They will have no brackets inside. If I add more and more of those, you are just encapsulating those with more indices inside, which is something that in machine learning is often used. This manipulation of dimensionalities, this is something that you need to know when you start doing classical machine learning operations. Principal components, things like that. You work with this a lot. Now, there are a few more things that you can do with indices here. So I have, let's say, consider this. And you can impose conditions. So create like a mask. You have like an array. I have an array 35. I reshape it 5 times 7. And what I'm doing here is asking for all the elements in that array that are bigger than 20. So the answer to that is another array with some values in false, some values in true. And I can use that array of booleans, of trues and false, to use it as a mask to just capture a portion of the array where those values are true. And that is pretty much what I'm doing here. Okay. More things here. Arrays from files. Many people use tables for storing data. So tables and but let's say the first thing that you do with tables is thinking about just numbers. When you are separating by tabulators or spaces, you make columns of values. That's one way of working. And there are some tools that allow you to capture and convert that into NumPy array. But many people uses are CSV files, so comma separated values. And at that moment, what you have is a file, and here I probably have an example of that. What is this in data? Why I don't have it here? Should be. No? Okay. I don't know what I have. What I have, a comma separate value. You can open that with Excel. For the small size files, it's okay. It's not a binary format, but it's okay. If you really want to use large amount of numerical values, you should skip trying to store those in CSV files. And I see people trying to use CSV files with more than 1 million rows, files of several gigabytes of size. That will not work. Well, that could work if you have enough memory on the machine, but you will spend a lot of memory just opening the file. It will be very inefficient. So for large amount of data, there are some other libraries like HDF, NetCDF for storing large arrays in hierarchical way, binary format, so very compact, very fast to read and write, all that. And Python, they have routines and libraries for manipulating those formats. So you are covered from that. But still, for small files, you can still use CSV file, or you receive the data in CSV file format. So this is something that you can use. Yeah, here I am using this routine in NumPy to load a CSV file. By default, the separator is a comma. Doesn't need to be a comma. And also you can select the number of rows that you are skipping on the top. And it will be reading this as a NumPy array, which means that all the elements in the array must be of the same type. So if you have columns, one of them with real numbers and some others with integer numbers, everything will be promoted to the to reals. And if you don't want to use that, the solution is to use pandas. And we will see that in a minute. Okay, so those are NumPy arrays created from files. And same thing, you can get some other elements. Where some of the files could be missing or not being a number. So that they will fill those elements in such a way that NumPy knows that there is not a number in that location. So there is the concept of not a number in NumPy. So in this case, I am taking all that. Okay. I probably will skip this universal functions. Okay. And I discuss a little bit that. Again, a lot of times when you're doing manipulations with NumPy arrays, you are not creating copies. There are ways to create copies. You can make a copy of an array. But when you are resizing, when you are slicing, what you are doing is a view. It's creating like it's the same array. You are looking into the same position in memory internally. And that is, I think, what I am doing here. And the copy version of that is with this instruction. With this, there is a specific method for duplicating an array, making a copy. So putting in a different location of memory in such that you can start manipulating that other copy without touching the original array. So this is not what is typically happening in NumPy. Broadcasting, oh, we are so close to the end of that. Let's see. Let me see if I skip this broadcast. Okay, this is probably more interesting. The functional programming side of NumPy. The idea here is that you want to use, you have developed or you wrote a function and you want to apply that function to all the elements in the array. So there are several methods for that kind of operation where the function is mapped to all the elements of an array. And one of those is this one, for example, and here I have like an example. I created a function that is taking the maximal, minimal, and the minimal of the element. And here I'm creating a test, like a simple array for shaping that. So this is the array. And I applying this operation here for all the rows in this array. And I can decide here on which row I want, on each index I want to operate. So if it's the index number 0, it will be across the rows. If it's the index number 1, it's across the column. So all that, the same operation. So taking, for example, all those first column here, and I'm doing the same thing. So I'm checking the maximum, which is 13, and subtracting the minimum, which is 1. So I'm getting 12. I'm getting 12, I'm getting 12, I'm getting 12. In all those elements, I'm getting 12. And taking by the column. If I select by this one, what I'm doing is taking the entire row here, taking the maximum, the minimal, subtracting. So you will see that all of them are 3, 3, 3, 3, 3. So the first one here is taking the corresponding element of each row. It means taking the column. So you are operating like the entire section here. The operation is for the entire column. And here you are adopting the opposite. With the index number 1, you are taking the rows independently. So which is the index where you want to apply that function. That is one of the operations where you are doing mappings. There is another, there's like this one here, where you are working with all the elements except for one dimension. So you have something that is n dimension, and we are cutting one of the dimensions. You have 3 dimensions, you are dealing with just matrices and operating with them. So at that moment, it's a little bit more complex. I have 27 elements here. I split those in 3, 3, 3, so you have 3 dimensions to work with. So my cuts will lose one of those dimensions. It will be just 2 dimensions. While here, I am going into just 1 dimension, which is in this case is trivial because I have just 2. This is just applying operation like the sum for an entire plane. Imagine that this is like a cube of values. Imagine like the Rubik cube. I am just making cuts and I am making the sum of all the elements. So all the elements here, all the elements here, all the elements here, depending on which is the index where I'm cutting, I am summing all these elements, and this is one of the answers. Summing all these elements, and this is the other answer, and summing all these elements, and this is the other answer. Or I am cutting such that I am summing all this square here and all this square here. So that is what I'm doing here. Okay. What else? Okay, same thing. I am defining a function. I have a NumPy array that it can take multiple arguments. I am basically vectorizing that function. The advantage of that is that sometimes it can take on parallelization of those. For this case, will probably not do much. Here, I have a function that takes two arguments, and I'm making, if one value is bigger than another, I'm making the subtraction, otherwise I'm making multiplication. I have here a couple of arrays, and I am here vectorizing this function. So this function, I can apply to those two arguments here, and I will be operating with all of them with sections of the array at once. Let me see. Let's try to skip this NumPy random numbers. Okay, a little bit of linear algebra here. The dot product here. This is, and I think that I already showed this. So I have the dot product here. And okay, but this is a good start. I skip a few things because this used to be much larger. And now I have to cut that in just 1 hour. To move to this one, to the pandas. Okay. So in NumPy, we were dealing with just arrays of elements of the same type. But most of the time, what you have are columns. And one of the columns is the age, which meant to be years, for example. Another column could be time. So you have another format for that. Another column could be height or weight, and you can count decimals. It doesn't fit very well the idea of a NumPy array for that purpose, because the columns define different data types. The proper tool for dealing with this sort of data is by using or consider that as a data frame. And Pandas is a library for data analysis. And the central object in Pandas is a data frame. They have also the concept of series, so series and data frames. But we will be concentrated for most part in the data frame section. As each column has its own data type, internally, very internally in Pandas, the columns in the data frame, in those tables, they are mapped to NumPy arrays. But the entire table is a Pandas data frame. So it's not directly mapped, but there are ways to map it to NumPy arrays if you want to do so, but not necessarily. So we start here. Well, Pandas is a project, has now several years around, and is very popular for data analysis, and people make questions about how to use that. So that is pretty much an invitation that Pandas is widely used for data analysis. For relatively small data analysis, I mean things that you can fit in memory that are not so big. When you need to do data analysis for extremely large data, so when you go into the realm of big data that is so big that you can no longer process that with the memory that you have available, there are some other libraries for dealing with that. And those libraries can interact with Pandas, that they can exceed in capabilities what you can do in Pandas when you're really dealing with big data. So the two main objects in Pandas are the series, which I will be touching very quickly, and data frames, which is the focus of this. So a series could be just, you can take it from a list, and that is a series. And you can index the series pretty much as you index an NumPy array. Now they have a data type. They have a type defined that they are a little bit more constraints on that. But a series could be anything. So it's a list of elements of the same type. So it's more than a list. It's more restricted than a list. And you can map that with indices. So you can have, for example, here, I have a few countries, and my dictionary is a mapping from the name of the country to the capital. So I am doing that for a few examples here, and I can convert that into a series, and this mapping is preserved. And so I can index the elements, and I can take the indices and the values. So, but I would like to use, so there are more things that are commented here about those indices, and see indices here. Okay. Okay. So I would like to skip this because I would like to concentrate in data frames. So a series is just one dimension list of elements that could have mappings to like a dictionary, but this time in a far more efficient way. And still, you need to preserve a certain data type for all the elements in the array. So you see, when you see the series, at the end, you see which data type is. In the worst case scenario, it's an object. So that means that all of them could be different things, but still. The most important thing in pandas, the central concept is the data frame, which is this. Let me see. I'm here creating a data frame first. No, a data frame. A data frame is a table. You have columns. Those columns could have a title. You can address the different columns with a name. And the elements in the rows can also receive a name. So it can be indexed. You can index the elements of there. So now we have here one case where I'm creating a data frame. This is like a minimal data frame from a dictionary where I have two columns and one element on each column. They're very minimal. And here I can ask, okay, what is the content of the first column? And it will say under the index number 0, I have the element number 1. So there is the concept of an index, and you can name the columns of the data frame from the dictionary, or if you import that from a CSV file, it can use the very first, the top row as the names of the columns. And I think that is what I'm doing here. So from a CSV file, so I have the same CSV file here. I have in this CSV file, there are the names on the very first row, and I have different values inside. And I can convert this into a NumPy array, into a pandas data frame. So this is what I'm doing there. The return of this is a pandas data frame. So here you have in bold the index. So that's one thing. That's one of the elements of the frame. You have an index, you have the columns, and the important thing is that the different columns could have different data types. This one is an integer, an integer, an integer, or several integers. But this one here in the all peak, this index here, is a real number. So you can preserve that. You can do that with pandas for data frames. You cannot do that with NumPy arrays. If you try to do this in a NumPy array, everything will be promoted to real numbers. The entire array will be of real numbers, which could be convenient or not. It depends, but that's a different. The data frames could be really big. There is no constraint on that. if you have a CSV file, you have a table, for example, in Excel, there are limits to the size of an Excel file. You cannot have more than 1 million rows on an Excel file. And there is also a limit on the number of columns, but I don't know out of my head how big they could be. In pandas, no restriction. If you can put that in memory, you can deal with very large data set and data frames. And here you can check, this is not that big, but you can check, for example, the final element, the final rows in my data frame. So those, if you ask for the first 10 elements, there is a method called head to look into them. There is also a method here called tail to see the final elements. And you have here the shape, which is the equivalent of the shape for a NumPy array. And in the NumPy array, you have the size of the matrix, so if they have multiple dimensions, all the number of elements under each dimension, on the size of the NumPy array of the data frame, or you can pick specific columns. I just want to look into those 2 columns. So you have many columns, and you can just pick all the elements. This means all the elements on 2 specific columns. I want to see side by side the age and the sex. Here described binary way, 0, 1. Okay. Now, in this data frame, you can also add columns, something that is hard to do or will imply to the creation of a new NumPy array. In the case of pandas, you can stack more columns to this. No problem with that, without my big penalty to the performance of that. So here I'm adding a new column. By default, it will fill that with nonce, which is like a way of saying I have nothing stored in that place for that column and that index. Or you can have a new column here. What is the new column? Okay. Here I am deleting the column. I am looking back to the original data frame and morphing. Okay, this one here is showing you that, what is the age here? Okay. Here, I am taking one element. If I am asking for this, it's a little bit like the views that we have in NumPy arrays. We are not creating a copy, making df1, putting a different name equal to another data frame or a portion of data frame. You are just making a reference to the same data. So any modification that you do to that data frame, you are doing it to the original data frame. So here you notice here is 63, and I adding 1. So here I am modifying the original, the DF, the original data frame is modified. And this is the content of the original data frame. The original CSV file, sorry. The original CSV file was like this. The pandas will interpret those as the name of the columns. It will use that. And it will read all that and assign the proper type for that, for the elements of the number, for the elements of the data frame consistently. There are ways also to skip rows, pretty much as we did for the NumPy array, taking some elements, and at that moment, the names of the columns will be the next row that was left after you cut the rows. Doesn't make sense in this case, but that's something that you can do. another alternative that is often used to recreate, store and recreate pandas data frames is using JSON files. JSON files are a little bit like the XML files, so they have an hierarchy to them. But in some cases, due to the complexity of the structure of the data, JSON files work much better. You can have a much richer structure in a JSON file, and that you cannot attain with a CSV file, which is kind of more restricted. And in the string scenarios, you can take the tables directly from SQL database or from the SQLite database. And you can use SQL, will not go into all that, to address or pick the elements directly from the database, so making queries to recreate the data frame. And thanks to another library that I think I always put it on the cluster, so probably is there. You can also read directly Excel files. From an Excel file, which is a table, you can pick up a data frame. And now to write the data frame, you have pretty much the same tools. You can write those as a CSV file, as a JSON file, and using some other libraries, you can put those files in some special formats, like Parquet, that can be used for big data analysis. For example, if you use a Spark, Apache Spark or something like that. At that moment, the storage of that could be parallelized. So that means that different machines could have portions of the data, big databases. So that could be multi-terabyte. And you can spread that whole table across multiple computers that will communicate to each other to do the analysis. Pandas is not capable of going beyond that. At that level, it cannot parallelize multi-node parallelization. It's not able to do that. You need to use Spark for such things. But there is still ways to transition portions of the data from there to pandas, manipulate that if the data is small enough. That's something that you can do. And let's see what we have here. I have here again views of a data frame. So portions of the data frame, first elements, the final elements. Here the first three, the last three. Here I have information about the data frame. Each column in the data frame could have a different data type. By default, it will select something like this, integers for 64 bits. You can change that. All are integers. Remember that all those are integers except for one column that has this column all picked here. That is a real number. So you see here, that particular column is a real number. And when you ask for the info or just the first elements of the array, it will tell you the data type of each column. So that is very specific for NumPy, for pandas. Okay, another thing that happens a lot is missing numbers and wrong numbers. Missing numbers are places in the tables that you are using to capture the data where there is no value defined. Okay, that's one thing. Worse than that are things where you have values, but those values doesn't make sense. For example, negative age. What is the meaning of negative age? So there are tools in pandas to detect or suppress rows where you have missing values. For example, here I have a data frame that I took somehow, where I have a few rows here where I have missing values. So I can use here, let me see. here, where I am picking just certain rows that fit a condition. For example, in this case, I want someone with an age bigger than 50, and this is, well, cholesterol probably, bigger than 150. So I can get just those rows that fit that purpose. And I think I'm going to, okay. And here is the function that allow me to remove all the rows where I have not numbers, where I have missing values. I can suppress those. And I can also count how many they are and see if it makes sense to suppress those with missing, where I'm missing something. Or making a subsection or a subset or like a sampling. This is not something. This is taking all the elements that fulfill a condition, a double condition actually. Bigger than 50 the age and cholesterol bigger than 150. What else I'm doing here? Okay, I can take this for this extraction of the of elements. The index is preserved compared with the original table. But if I want to work with them as a new index for them, it will re-index those. It's not making a copy again. The values are the same. If you change anything here in this data frame, you are changing the original data frame. But at least I can work with them from 0 to whatever is the number of rows that I have. So it's just a re-index. So inside pandas, the different columns are NumPy arrays. There is like information about the indexing. And if I remap the indexing, it will create like a map. Okay, the index number 0 is equivalent to the index number 63 in the original data frame, and it will pick the elements that way. So they kept that information inside, so you can address the elements. It can do things with dates. You can suppress invalid dates. It can try to understand the meaning of the dates, year, month, and you can define how you're supposed to interpret the value of the date. At that moment, the data type for that column will be a date data type. Let me see if I have one example here. Okay. Removing duplicates, another thing that you can do, if that makes sense. You can check for all the cases that are duplicated. It will basically return true or false if that particular row is exactly the same somewhere else in the data frame. It will make the comparison, and you can decide, okay, I want to suppress that. I want to drop the duplicates. There is another function here for removing, keeping just one. And now you see here, I have 303 elements. After you remove the duplicates, I lower to 302 elements. Here is the original one. Merging, so you have two data sets and do two data frames, and you want to collect those, you can do that. When it will check the names of the columns, and it will probably align those columns. And if it's one of the data frames contains some column that is missing on the other, it will fill with nonce those that are missing. So maybe I have something like that. Yes, I have something like that here. So I have here one data frame that contains book, and here I have another data frame that I'm creating on the fly here, where I have a few values here for a new column called new book, one new book. And this new data frame is called new book. When I merge those, I I am filling with nuns when not a number for those that are missed. Another thing, and unfortunately, I skip entirely the element, the information about matplotlib, but in pandas, there is some facilities to call matplotlib and say, okay, I want to make a plot of this column versus this column. And you can name those columns explicitly. So that pandas will check that and will send the proper instructions to matplotlib. But you only need to address those by the column name. So that is what I'm doing here. Here I am plotting the age as an histogram, and I only need to say, okay, I need a plot, a histogram plot of the age, and it will produce that in the background using matplotlib. Okay, or something more interesting, taking all those pairs of values, so you have multiple colors. This is something that you do very often when you have multiple dimensions. I want to compare the different columns. So in the diagonal, you will have the histograms. In the non-diagonal values here, I am comparing, for example, let me see, what is this? This 3 BPS compared with this TH, like this cholesterol, whatever, versus the H. So here I have the different values of cholesterol versus the different values of H in this plot. So I can see correlations between the different values from a very visual point of view. If you want to go deeper than that, there are techniques in machine learning for selecting which values have correlations or which of those columns are less important than the others. So making a decomposition in the principal components. So those are things that I probably will show you later. Now I think that my time is okay. Maybe I can do, okay, what I can do this. Okay, now that I have some time, that was not that good time. This supposed to be before this, but I will just want you to show you very quickly matplotlib. I will not go into the detail. This is supposed to be before the pandas stuff. But anyway, so between NumPy and pandas, I show matplotlib, which is a library for making plots. Simple plots, you have a NumPy array or something that internally will be converted into a NumPy array, like this. Here is an explicit NumPy array. It doesn't need to be like that. It could be a list. Internally, matplotlib will convert that into a NumPy array, and we use it to create the plot. So simple plots, subplots, and those subplots could have combine the same X dimension. With matplotlib, you can really produce plots that will go straight for publication. You can put equations inside. You can make them from different colors, different symbols, different glyphs for representing those histograms. And now you see that I able to put some elements in with Greek letters, equations. I think probably have equations. Let me see. Or divide the sections in multiple ways. This is, let's say, oh, we see, oh, I didn't have the symbol here. I think I have symbol here. Let me see if I can run this. And beyond Matplotlib, there is another library that is called Seaborn. And that Seaborn is like a Matplotlib for data analysis or for data science, which allow you to do certain kinds of usual plots, like those violin graph kind of diagrams, those with uncertainty bars, all that sort of things, directly using Matplotlib. They are optimized for those sort of things. Let me see if I can do this. Oh, there is something I need to fix it. Anyway, so this will be closing the materials that I have. Again, all this in these notebooks. I think I put that the clone for the notebook for making the scripts. I think that we finished a little bit earlier today. But that's it. Thank you very much. If you have questions, just let me know something specific or that you want to see. And otherwise, next week, we will be covering something different. In the afternoon sessions, it will be partial differential equations, codes that use partial differential equations. And in the mornings, it will be a continuation of the big workshop, Introduction to HPC, how you submit jobs, how you use a terminal multiplexer. And the final day, it will be a little bit of math, machine learning, and deep learning. So I will be using this a little bit, but I will not be assuming that the material of today. So it's slightly different. Otherwise, thank you very much, and see you next week.